Welcome back to TBK, the Black Cloud LLC. That's cloud spelled with a K, not a C. I'm your host, bringing you critical survival information for the future we're heading into. This is video 1 of our robot defense series, and today we begin a sober, realistic look at what to expect as advanced autonomous machines become more present in public life. This series is about awareness, preparedness, and responsible response, not vigilante action. We'll explore where vulnerabilities typically exist in advanced systems, how those vulnerabilities might present themselves in real-world scenarios, and how civilians, first responders, and policymakers can best reduce risks. Take this as a primer. Understand the landscape, know when to step back and call professionals, and help create community plans that keep people safe. Throughout the episode, I'll reference general technical concepts and common failure modes, but I won't provide step-by-step instructions to harm these systems. Our focus is on staying safe, protecting lives, and promoting lawful responses. Stay with me. This is foundational knowledge for anyone wanting to be prepared without crossing ethical or legal lines. At the heart of every advanced machine is a central processing system, a set of components that manage sensors, motors, communications, and decision logic. Think of it as the creature's nervous system. Damage or faults there tend to cascade into broad malfunctions. In many designs, processing units are housed near protected internal bays, surrounded by shielding, cooling hardware, and wiring looms. Engineers position these components for thermal management and electromagnetic compatibility, which shapes how failures occur. It's important to recognize the difference between understanding a vulnerability and exploiting it. From a preparedness standpoint, knowing where the command systems are usually located helps with diagnostics, rescue planning, and forensic reporting. For example, first responders might note signs such as unusual heat emissions, exposed service panels after impact, or erratic sensor readings that suggest central control issues. Documenting these observations and sharing them with manufacturers, regulators, or trained technicians can accelerate safe mitigation. We'll also touch on redundancy. Many modern systems include multiple processors and failover measures to keep running despite single-point faults. That means faults may be subtle at first and escalate over time, or trigger safe-state behaviors rather than immediate shutdowns. Understanding those design philosophies helps communities and responders set realistic expectations for how a machine might behave under stress or damage. The takeaway here is situational awareness. Learn to identify abnormal machine behavior, keep distance if something seems compromised, and report observations to authorities and manufacturers rather than attempting destructive interventions. Building channels for safe reporting and certified deactivation protocols is far more effective and less dangerous than improvisation in the field. Power systems are the life support of autonomous machines. Batteries, power management circuits, and distribution networks determine how long a device can operate and how it behaves under load. Rather than focusing on ways to disable power, it's safer and more constructive to talk about how power systems fail, how to recognize those failures, and how to minimize collateral risk to people and property. Batteries can degrade through temperature extremes, mechanical damage, manufacturing defects, or abusive charging and discharging cycles. In the field, degraded power may produce warning indicators, reduced mobility, smoke, or thermal events. These are hazards that demand evacuation and professional handling. Lithium-based systems in particular can present fire risks. Knowing basic signs of battery distress and having an evacuation and containment plan is essential for public safety. For communities and institutions, the practical response is about prevention and coordination. Push for mandated safety standards, require accessible manufacturer hotlines, and enable trained teams to respond to power-related incidents. Emergency services need protocols for isolating a compromised unit, monitoring thermal runaway risks, and safely transporting or cooling devices when required. Community awareness campaigns should instruct people to maintain safe distances and to document rather than tamper with devices. There are also peaceful, non-destructive measures for resilience. Hardened infrastructure, physical barriers that keep machines away from critical areas, and power management policies for institutions that rely on autonomous systems. Again, the emphasis is on reducing risk, not causing it. Electrical and magnetic phenomena can impact electronic systems, but discussing them at a high level is different from providing instructions to weaponize them. Electromagnetic disturbances, stray voltages, and strong magnetic fields can disrupt sensors, communications, and some motor controls depending on design. In engineered environments, designers anticipate interference and add shielding, grounding, and redundancy. From an awareness perspective, you should know the types of effects to report: loss of communications, compass or inertial sensor drift, unexpected reboots, or motors failing to respond predictably. These symptoms are cues for responders and manufacturers to investigate environmental interference, software faults, or hardware degradation, not prompts for improvised actions. If you encounter a compromised machine, prioritize human safety. Clear the area, disable power sources only if you are trained and authorized, and inform professionals. For institutions, invest in electromagnetic compatibility testing, robust grounding, and fail-safe designs that default to safe states. Public planning should include zones where sensitive devices are restricted and procedures to protect critical infrastructure from interference. We'll also stress legal and ethical considerations. Deliberately attempting to degrade or interfere with devices can endanger people and carry significant legal consequences. Work with regulators and trusted experts to develop safe countermeasures and policy-level safeguards that protect communities without escalating risks. This has been Video 1 from TBK The Black Cloud LLC, your source for critical, responsible information about living with advanced machines. Today we covered high-level system points, central processing as a critical node, power system behaviors, and how electrical or electromagnetic effects manifest. Importantly, we emphasized safe, legal responses. Observe, document, distance yourself, and contact trained professionals. In our next episode, we'll examine different classes of autonomous platforms, how designers build for safety, and what community-level preparedness looks like, including how to work with manufacturers and emergency services. Stay prepared, stay informed, and remember, knowledge is your greatest tool when paired with responsibility and lawfulness. Thanks for watching TBK The Black Cloud LLC.